1/2 u plus u times v.
Excuse me. Is that right? No, I'm sorry. It was muted.
I see.
May you start from all over. I'm sorry.
It's okay. Okay, so we'll start with doing this computation, how to find the algebraic boundaries of the example in the morning. So let me recall, we are considering the unit wall in R2, and then we are considering the image of this unit wall under this polynomial map that was given that u and v mapped to so 1/2 u plus u times v and 1/2 v minus u cubed. So, and we discussed there's like these two different kind of boundaries, one coming from the like the folding of the map and the other one coming from the boundary of the unit wall. So let's do the folding, like how to find algebraic boundary from the folding. So first we consider polynomial ring in 4 variables. So u and v correspond to like the coordinates in the pre-image space and x and y in the image space. And then we define these polynomials f and g that come from the polynomial map. So these are exactly, the coordinates of the polynomial map that we consider. And then we define the parametrization ideal. So, and what the parametrization ideal means that, so now we recall x and y were the coordinates in the image space, and x will be equal to the, what's given by the polynomial f, and y is given by, what's given by polynomial g. So this is the parametrization ideal. So this is something that comes up quite a lot in computational algebraic geometry. And then, sorry, and let me do the computations at the same time so that you can see what's happening. So let me restart. So this is the polynomial ring, polynomial 1, polynomial 2, and this is the parametrization ideal. And next we will compute the Jacobian of this ideal, but let's note this, we actually want the Jacobian in u and v, but because we have four variables, so the Jacobian has 4 rows because we have 4 variables and 2 columns because we have 2 elements in the ideal. And actually, we are not interested in this like lower part. So what I'm going to do, I'm going to get rid of the last 2 rows of the Jacobian. So this is just the Jacobian corresponding to the parametrization. And now we're computing what's called the ramification locus. So the ramification locus is given by the points where this Jacobian drops rank, but only of the points in the ideal. So you see here, this ramification locus is defined as the I was this parametrization ideal plus them 2 by 2 minors. I mean, in this case, it's determinant actually. So plus the determinant of the Jacobian. So let's see. So when we compute it, so it will consist of 3 polynomials. So 2 coming from the parametrization map. So the first 2 are exactly what we saw from the parametrization ideal. And then this is like this determinant of the Jacobian. And then to get this, we still live in this, now we have polynomials in 4 variables, u, v, x, and y. But we want to get rid of u and v. We want to describe something in the image space. We want something going in x and y. And how we get it is we do the elimination of the variables u and v. And you can see that the result is polynomial that's only in x and y. And so this is this. Let me see if I have the picture open still. So you can see lots of colorful pictures. Listed figure 8, right? So the one that we computed right now is this curve. Sorry, that was the folding. So this is this curve over here where the folding happens. Do you understand what why I say folding? So you should imagine this. This is like a pancake, and then you like flip half of the pancake. So that's what's happening. And this is like where this flipping happens. Okay. So that was one part of it. And the second part is we also have to compute the part that comes from the boundary. And actually, it's easier than what I said in the morning. So we just take the polynomial that's defining the unit circle. So u squared plus v squared minus 1. And we add this polynomial to the IDO that was defined by the parametrization map, because we're just actually interested in the image of the unit circle. So it's nothing else in this case. And then we want to eliminate u and v again. So this is actually much quicker. Now, if you can see, I have the participants list for some reason. Can't see myself. Well, and yeah, so now you can see again an idea which we generated by 3 polynomials, and then elimination gives this degree 6 polynomial that's like the boundary that comes from the unit circle. And this is like a general method how to compute these algebraic boundaries. But it's not necessarily always like this as I wrote here. So it could be, let's say, we would have a unit ball in 3-dimensional space, and we would map it to a 2-dimensional space. Then it won't be enough to consider for these boundaries to take the u squared plus v squared plus z squared minus 1, because the boundary is 2-dimensional. So it won't map, unless you have something very special, it doesn't necessarily map to a 1-dimensional boundary. Then you have to consider also the ramification locus in this case.
Which theorem or which result guarantees that you can always eliminate this in terms of x and y?
Well, I mean, you could get something that's empty set, but the elimination, this is like this. How it's defined is you take the. So what is the elimination do? If you have an ideal I in the polynomial ring with n variables, then the elimination ideal, and now I probably get the indices wrong. How do you eliminate usually? So IL is the intersection of I with the polynomial ring. I think it's like this, from xl plus 1 up to xn. So it can be empty, but it's always defined, right? If it's empty, then yeah. I mean, it shouldn't be empty if something actually maps to something that gives boundary. And so this is what's called the elimination ideal. And then the main, like, let's say, the fundamental theorem in the elimination theory is that you can actually compute it. So it's not true that you take a generating set of I and intersect it with this polynomial ring, and then you get the generating set for IN. So this is not correct. You have to take a Kröger basis with respect to elimination order. And then if you intersect the Kröger basis with this polynomial ring, then it is true that you get the generating set for IN. So this is defined for any ideal, so the elimination ideal. but yeah, it could be, sorry, when I say empty set, I mean zero. Yeah. It won't be empty set. It's an ideal. Are there any questions about this computation?
Maybe a few words about the ramification.
So basically the main idea of this comes from the implicit function theorem. So, and implicit function theorem says that if you have something that's defined by like implicitly, like, you know, given that some polynomials are set, so let's say you have, now I'm going to use different variables, but let's say you have some polynomials f1, and I don't remember what the indices should be, but let's say in this case we have 3 polynomials, so let's do this case. U, V, X and Y. So we have 3 polynomials in these variables that are set to 0, right? So this means we're something like is given implicitly, and the implicit function theorem says, so now I'm like, if you consider the Jacobian, and if the Jacobian has maximal rank, then in some neighborhood, so how is it? You can write X and Y, is it uniquely in terms of U and V? So I think this is how it goes. And the ramification locus is where the Jacobian drops right. So this won't be true anymore. That, but I'm saying something wrong because actually we are considering the Jacobian only of the parameterization map. So without, yeah, so sorry, I'm doing something wrong in our case. We consider the Jacobian of the map of this map, I think, right? So, I mean, I added this F3, that's already the determinant, but we consider the Jacobian coming from these polynomials. So this is where this idea, so, and ramification, like, also means, so how is it? Yeah, so in this pancake example that we call, so, and I'm probably not able to draw it very well, but here there is some folding happening, right? But basically, the points over here have 2 preimages. The points over here have 1 preimage, and like this is like the branching locus is where it like changes. Any other questions about this example? I can also share the code later if it's like, if it's useful.
Any question from IB Karachi side?
Yeah, any question from IBA Karachi side? I do understand that there are many students who are working on computational algebraic side. So probably, yeah, okay, if there is no, okay.
Okay, then in the rest of the tutorial, so now you're going to do the work. I have written down 3 exercises. So they are exercises that have appeared. So the first one, so actually I recommend that we start with the second one because I think this is the most important. And let's say maybe the first one we leave to the last one, but I wrote them in the order that they appear. So the second one is to prove the 3 properties of non-negative rank that we saw. so that non-negative rank is greater or equal than rank. Rank of M is minimum than its of its dimensions. And if rank of M is 0 or 1, then non-negative rank is equal to rank. So I suggest that we start with this problem. So, and then in the second lecture, we had this, so this is basically about understanding the definition of a finitely generated cone. Why it follows if every column of a matrix is in cone of W, then the cone of X is in cone of W. And then finally, at the very beginning of that first lecture, I said that prove that the rank, like I gave this characterization of rank, and like that the last problem is to prove, you know, it's this definition is equal to your favorite definition. And so I suggest that we all, like, you can work alone or together with who is next to you. You know, I will walk around, and then at some point we will write down, like some of you can write down some of the solutions, but we don't have to go through all the problems. So now is your turn to actively, you know, work on these questions.
Naman, screen share band kar, so that IBA Karachi can view the question, the exercises which is being proposed by Professor Kubjas. नहीं उनको
It can go.
we will okay, they can share. Exercises नहीं आ रही नुमान, exercises नहीं आ रही.
Excuse me, Professor Kaie.
Yeah.
I have a question. Yeah, I'm from IB Karachi.
Yeah. Go ahead.
Actually, the question is related to the rank and nullity theorem. We have a rank and nullity theorem in linear algebra, that is, rank plus nullity is the number of unknowns present in the system. So whether we could generate a rank and nullity theorem with this non-negative rank condition, whether that theorem for this non-negative rank condition must exist or not.
So did I understand correctly? So there is the null, about the dimension of the kernel and image, and if there's something similar for non-negative rank, then the answer is no. Well, I guess maybe something in terms of cone. So basically one has to think, you know, everything about rank is linear algebra, and this non-negative rank is really about cones. So I would have to think about it if there is like something, you know, about, I don't have an answer about this, but I will have to think about it. Maybe there is something analogous in discrete geometry about polyhedral cones.
Okay, thank you.
Yeah, at least from the, from the characterization. What about the other ones? Oh, it should be plus. Sorry. Here, of course, it should be plus. I mean, it's also true otherwise, but then it's to connect it to non-negative rank. Yeah, then now it's a little bit more difficult. Sorry? So I have updated the problem to B. It should have been that the non-negative rank of M is less or equal than M, and then of course the previous statement was also true, but we want to prove the statement for non-negative rank.
IB Krachi, everyone please note down these exercises, exercise 1, 2, and 3, and please put your hands on exercise 2. And similarly, just exercise 1 and 3, just have some discussion and get it done so that we can move toward toward the discussion again. Probably some segment of this section will be given to Shaheen to conclude a few of the things which are left over. And after the tea is at 3:30. So after the tea, there will be project discussion session at 4 p.m. Okay. Yeah, maybe in next. So maybe next 5 minutes, Shine will resume. Please note down these exercises, and you can contact Kubjas for any kind of discussion, maybe tomorrow as well. Today and tomorrow, we are here till 5 p.m. And there is an announcement that tomorrow there will be closing ceremony. I will announce everything in the morning. IB कराची वाले आप डॉक्टर जुनैद को मैंने मैसेज कर दिया है. इफ पॉसिबल तो दानिश को भी बुला लें. इट विल बी गुड कि जो लोग इंटरेस्टेड हैं इन हैविंग open project for the research or this इस किस्म की डिस्कशन में they all should be here. थोड़ी सी डिस्कशन थोड़ी सी इंटरैक्टिव हो जाएगी. You understand my point?
So work on the one case. You're right. All the same times there are metrics. It's not. And anyone, if you want to ask any questions, I could be around and like also after the discussion session, like, we can, I'm happy to discuss anything else.
Yeah. So this would be good to do these exercises and try to come up with the proof and then.
Okay.
Today we have planned too many things. Now we are heading towards, okay, as we promised with Shaheen that we will give her a little bit more time to conclude what is left over from the first lecture. So now over to Shaheen with some concluding things on the theory of Ulrich, Solomon, and Doric and Tirao ideal. Sorry.
Okay, thank you so much for giving this opportunity. Okay, so let me just recall that we have this. Now we are just okay. So about little bit more about the Orlick Solomon algebra. So that was just the exterior algebra portioned out by this Orlick Solomon ideal, which is actually generated by these ones, which are just corresponding to the hyperplanes, right? And okay, so here what I want to say is that I just want to say about the basis of this Orlick Solomon algebra. So the basis of the Orlick Solomon algebra is this one. If you will just consider, if you remember, you have already done this. You have already seen actually this circuits notion in Sarah's lecture, right? Circuits are the minimal dependent sets, subsets. So in our case, they are minimal dependent sets of subsets of arrangement, right? And the broken one is that one. You will just, if you have this C is a circuit, and then you will just drop out the maximum element from that circuit. This will be called broken one, which means that we are just taking an order on these hyperplanes. So this is the maximum for me, right? Okay, so this is broken circuit. So here, this is just, sorry, here is A, I1 up to IP. Let's suppose if this set does not contain any broken circuit. Okay. So for example, if you have fixed the linear ordering here, then you can see that you can just fix your basis element in your Orlick Solomon algebra. So for example, the example which we have already done, you can easily see that in that example we have n, and then we have here I n minus 1 ai n, right? So for example, you can see that these sets, which means that hi or int hn, these are the sets which does not contain any broken circuit. And other than that, if you will consider, then they will contain. So for example, if you will take h1, h2 here.
Shaheen, they're all monomial. AIP.
No, they are the exterior product here. So I just have, I have already, I am
Okay,
using the same notation,
okay.
which I have
exterior
already
algebra.
described in that lecture.
Okay, this is the exterior setting. So
Yeah,
these are all
this exterior
monomial,
setting, yeah.
exterior monomial. Right.
Exterior monomials.
Okay. In
Okay.
monomial algebra, we call it the standard monomial in monomial algebra. So if I view this thing from the
Yeah, you
monomial
can
setting,
also say that the standard one, if you will just consider this relation. I mean, standard one means that you are just taking the order relation between sets. So that is not
no.
sorry.
The standard one is this. Okay, every monomial ideal can be viewed through the lattice, like x square. For instance, I take the monomial x square.
Mhm.
So the monomial which are very near to x square, that means x square divided by x. If I write x square y square, so
Hmm.
the standard monomial are the one which are obtained by dividing that particular monomial by single power of x or single power of y. They're all called the standard monomial and they form the K basis. This is the Macaulay basis theorem. And in this particular case, the broken circuits are the one you are dropping just one vertex from there. So they are the standard monomial, but you are taking those and again, you are considering those monomials which are
Okay, let me just.
not in the broken circuit. According to me, it should be in the broken circuit.
No, it does not contain any broken circuit. Because here we are just considering the dependent set, which means that we are just removing this part. So that's why here you will consider your monomials, maybe in your language monomials, which does not contain, I mean, the corresponding indices does not contain any broken circuit. Okay, so this is just the corresponding example. And before that, I have already said that.
So in this case, they are going to be the maximal independent set, right?
So for example, this one is broken circuit. Because if I will take this thing,
so if one
this is a
want to
circuit.
view, if one would like to view it through the independent and dependent relation, so the minimal dependent set, if you drop any of this,
Okay,
so
so
it,
the
you are in the
okay, so what are the circuits are here? Circuits are the minimal dependent set, which
Yeah.
means that the circle contains only 3 elements in my set. So circuits are just the 3 subsets of
in R2.
array.
If you are in R2,
No, I'm just talking about here. This cardinality is n.
oh, okay.
So any 3 subsets are circuits in our case. If
Okay.
I'm just considering this example, so be careful. You have this central arrangement in
Okay.
C2, right? So this one is a circuit for me,
And
because
then
if I will remove this one, then definitely this will become a broken circuit.
Broken circuit. Okay. Independent set.
So that's why that's why you will just consider all these terms. If you have chosen your maximum is this one, and I mean it's depending on the ordering as well. If you will change the ordering, then definitely you will have some different answers. So you should be very careful what you are choosing, what you are taking the order in those hyperplanes, right? Okay, so this is the final remark about the Ehrlich-Solomon algebra. You can view, I mean, you can just, if you have the broken circuits. So this basis is called usually non-broken circuits because these bases does not contain any broken circuit, right? Okay, and it's usually, of course, because this gives you the cohomology algebra, so it's very useful to just have this one to count and so on and so forth. Okay, now let me, as I have said many times, for each arrangement, we have this metroid, which is called the underlying metroid of the arrangement. And here the circuits are, because we have many definitions of metroid, how we can define the metroid, we can define through the circuits as well. So if I will say that, what are the circuits in this case? So this means that I have so the circuits are here, the same circuits, the minimal dependent subset. So here the underlying space you can consider just 1 to up to n corresponding to each hyperplane, and there is order because if you want to define the broken circuit, or then you can just have this order here. So this is the minimal dependent subset in, and the broken circuit is similar one. Okay, so now what we can do, and so one can see that one can define these Ehrlich-Solomon algebras for any metroid, because you don't need anything in that case, because you just need to see that how, what are the dependent or minimal independent sets there are there. So it's, you can just take out from the arrangement and you can just generally define for the metroid as well. Okay, there is another thing. Okay, so this is the metroid and here the circuits are this one. That's perfectly fine. But we have another thing which is combinatorial setting, which we will call this one, is called the broken circuit, which is associated to this. Maybe you can say with the arrangement, or maybe generally you can say just with associated to the any metroid. So I can write here this just for any metroid. So if you have some ordered metroid, so you have this circuits, broken circuits. So what is this? This is the simplicial complex. Right, and its spaces are subsets of E does not contain any broken circuit. So one can associate this simplicial complex, which is called broken circuit simplicial complex. You can associate to every metroid and as well as to every hyperplane.
Okay, so the metroid, the basis of the metroid would be?
The faces. Faces are the subset that does not contain any broken circuit.
May you please write it down?
Sorry?
What are the basis of this metroid?
Basis, okay. The maximal independent
Set,
yeah.
maximal independent.
Maximal independent.
So they are the broken circuits?
So broken circuits are just the minimal dependent subsets of A.
Broken circuits are independent one.
Oh, sorry. Broken circuits are the circuit minus the maximum element. That is called the broken circuit.
Yeah.
And here we will just consider those sets which does not contain any broken circuit. So for example, if I want to see that for this arrangement, what is my
That would be good to
complex?
do one example.
So this means that your simplicial complex is just containing these elements. 1n, 2n, and so on up to n minus 1n. So this means that this is a point n 1 to up to n minus 1, and this is 1. So this is the broken circuit simplicial complex in this case, right?
Shaheen, how? I didn't get it.
Because these are all sets which does not contain broken circuit, which we have already seen in this part, because I said that this is actually the basis for this Ehrlich-Solomon algebra.
That's why you are.
So that's why you have all these sets which does not contain any broken circuit. So your simplicial complex will be this one.
So that's
because
why
these
you are
are
always
faces
dropping, yeah.
in your simplicial complex.
That's why you are dropping n every time. The maximum.
Yes, maximum. I mean, either if you can work with the minimal element, then you need to add every time 1 if you have your minimal element is 1.
And if somebody think why not 1, 2 is there, so what is the answer?
Because 1, 2
Yeah.
is broken. 1, 2 is broken circuit.
It's a problem. Okay, due to the okay. Yeah, perfect.
Okay, that's good. Okay, now we will see the connection between. So you know that there is some algebraic connection between the simplicial complexes and the algebra. So we know that there is a very standard ideal which is associated to every simplicial complex. So that's why we will have a course for this simplicial complex as well, and that is called the. Let me just write here in this way. This is the Stanley Reisner ideal of this one. Right? And what is that one? It's generated by, do you remember?
Those which are not inside.
Non-faces elements of okay, this is just generated by minimal faces. Maybe I can say
Minimal
that.
non-faces.
Minimal non-faces. This is in this one. Okay, and you know that you know about this ideal that it is always monomial one, right? And in this setting, definitely we don't have this ideal, but we have in the symmetric setting, we have the Orlik-Terao ideal. Remember? This one was just, okay, so let me just recall that one. What was it? By IT, where this is just a relation between the hyperplane. But this is not monomial ideal in general. So, but there is some connection between them, which is by Proud and Bayer. So they said that, but you know that there is an ideal which is I mean, for every ideal there is an ideal which is associated to this one, which is monomial one, and that is comes to the Grabner basis. And generally we will take this initial ideal of this ideal is actually nothing, just this Stanley-Reisner ideal for this broken circle. So this is the connection between this ideal and these simplicial complexes with the monomial one. And this gives, and furthermore, one more result in combinatorial community algebra is that one, this broken circuit simplicial complex is always shellable. This is some geometric or maybe some its definition is like constructive one. So it's saying that if you have I mean, it's okay, let me just recall, because whenever you have simplicial complex, this is always generated by S, and you just need to pick some ordering of these spacers such that it satisfies this condition, is that the union of I is equal to 1 to T with intersection T plus 1, its dimension is less than dimension of f of t.
F of t plus 1 minus.
-1. Okay. This is the sort of the definition of the shelling.
Stand by the
This.
union get.
Okay, okay. It's fine, it's fine. So this is called shelling. If you find such order in your facets, this is called shelling, and your simplicial complex is called shellable simplicial complex. And it is very well-known result if you have shellable simplicial complex, then its associated standardized ideal is always which means that the depth and the dimensions, they are same, right? So you have studied lot of depth and dimension in this case. How you can calculate the depth for the ideals, and if this is same, then definitely it's called Cohen-Macaulay, and if this is true, this is actually if and only if result.
One minute.
Sorry.
Shellability implied only. 1 minute.
Okay, sorry. Yeah. Okay. Another result which I will use from the commutative algebra is that one, if your ideal is, which is actually the initial ideal, because this is nothing just the initial ideal of our this Orlik-Terao ideal. So this means that this is Cohen-Macaulay. Whenever this is Cohen-Macaulay, so this implies that your is also Cohen-Macaulay. So this means that this is every time whenever you are considering the Orlik-Terao ideal, this is always Cohen-Macaulay, right? Okay, so now the questions are about what we can say about this ideal admits any linear resolution or not.
Find linear resolution for participants.
Okay, so I think okay. Let's just I will describe the P linear resolution. Some number here. P linear resolution. So you have started from this one, and then you have. You have already seen the minimal free resolutions. Oh no, sorry. There are some. And yeah, that's it. So if you are familiar with the minimal free resolution, right? So this is if your minimal free resolution is of this type, then it is called P linear resolution. So this is some minimal free resolution in for this ideal.
This is a special kind of free resolution where the shift is
It's just
increasing
the
by
single,
1.
yeah, it's by 1.
So at first step, this is minus p, and then p plus 1.
So okay, let me just write here the Batty numbers instead of writing this sum. Maybe B0, B1, and so on. Right? It's better to write this one because every time you will get just the copy of the same shift. Okay, so let me just. Okay, so this means that now we are talking about when this ideal admit linear resolution, which means that, but we know that our ideal is always Cohen-Macaulay. So we can see that if your ideal is already Cohen-Macaulay, so when this admits the linear resolution. So I'm just to write a result which is generally hold for monomial ideals, then or actually the graded ideals, which is Cohen-Macaulay. So this result is by actually and independently by Vale and these are 3 1, and then we have Venkaria and Villara. Right? So this theorem says that if you have the graded ideal, Okay, graded ideal, and which is point we call it because we are now in this setting. In our S, right, of 4-dimension H, because everything we know that here the co-dimension we know that what is the co-dimension, our ideal is n minus the rank of A. This co-dimension, right? Okay, so in this setting, and let P be the smallest. Integer such that IP is non-zero. Right? So from where we have started, this is the initial index. So then the following are equivalent. So we say that I has P-linear resolution if and only if satisfy this condition, which is in terms of okay, so let me just write in terms of the Hilbert function, IT is same as the Hilbert function plus H minus 1 P, where this is Hilbert. Sorry.
This is not the way. Yeah, it's a number.
So this means the monomials of degree P, right? And the other thing is you are also have seen a lot of regular sequence in previous lectures. So for any maximal regular sequence, so let's call F1 up to Fn minus H of linear forms in S. This quotient ideal is same as the maximal ideal power P. I mean in the quotient ring. So we are talking about they are equal in S over F1 in this quotient ring. This M is the maximal ideal in S, right? So if it satisfies one of the condition, then we will say that it has P linear resolution, right? And now I will just I will not take too much time. So I will just translate this result in terms of my ideal. So this is by A and in normal. So for essential central arrangement with n hyperplanes, so essential means that the dimension is same as the rank of the arrangement, right? So in this case, this one, the Ehrlich-Tarrant ideal has P linear resolution. If and only if, so here P cannot be 1. And A can be written as the product of two hyperplane arrangements where one is generic central arrangement of n minus L plus P. L is here the dimension or the rank, hyperplanes in up p-dimensional vector space. A2. So you are familiar with this one. I have already defined in first lecture what is the meaning of the generic or the hyperplane arrangement in general position. Both have the same. Okay, so A2 is the Boolean arrangement. In R minus P dimensional vector space. And this actually arrangement can be seen as the or we can obtain this by the Koning construction. Recursively, we will do the Koning construction again and again, and we will get this one. So we can see this one in this way as well. This A is obtained by simply Koning a generic central arrangement of n minus r plus p hyperplanes in p-dimensional vector space. So you will do this step L minus p times you will do this Koning construction again and again. Right? So this gives the characterization of arrangements for which your Ehrlich-Tarau ideal has linear resolution. So there are many other questions. So I will just stop myself by pausing this conjecture. One may say that I didn't define this this arrangement, but I can explain in the problem session what is this arrangement is. So an arrangement is super solvable if and only if Ehrlich, let me just see Ehrlich-Tarau or Ehrlich. So Ehrlich-Tarau is causal algebra. I mean, this is another algebraic notion.
Is it generated by binomial?
Sorry?
Generated by binomial?
No. I mean, they are generated in the they have the basis with respect to that field or that algebra in quadratic. No, if that is true, then it is causal, but the converse is not.
This direction.
I mean, quadratic basis implies causal.
This is not if and only.
In general, that is not. Okay, any questions? So, no, I have already taken enough time. So, is there any question?
This is the conjecture by whom?
It's by Uzvinsky. I mean, this was, yeah, he. I mean, let me just add one more remark, because we can also ask about the linear resolution of the Ehrlich-Solomon algebra, and they also have this linear resolution, and they also satisfy some sort of this kind of condition. I mean, if your arrangement satisfies this condition, then the Ehrlich-Solomon algebra has also linear resolution, and that is done by Uzvinsky and I don't remember the other name. It's a big name, but
Question.
Yeah.
Abe?
Huh?
Abe?
David Eisenberg.
Eisenberg, okay.
Yeah.
Very big name.
Yes, that's right. So that's done by done for the Orlick-Solomon algebra. Has linear resolution. Okay, any question?
Any question from the IBA side? Numan, IBA की picture दिखाना जरा. Any question from your side, the present audience? Okay. If this is the case, let's. Oh, what happened in IBA? कहाँ चले गए सारे? Okay. 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 If this is the case, let us thank Dr. Shaheen for her lecture. This concludes her quota of lectures. Thank you, Shaheen. Thank you very much. It was super quick, but definitely the topic is quite rich in the sense of combinatorics and as well as in algebra. So at least one thing what participant can take, they have the understanding of just basic understanding of the keywords of the hyperplane arrangements and how this hyperplane arrangements link with various structure, standard as a ring, and then metroid theory. Then you have seen a lot of other things and topology, algebraic topology, monodromy. A lot of things are there. So this is very, very rich area of research. And I think from these lectures, you have some understanding, some fundamental understanding of the topic. So thank you, Shine. Thank you very much for your lectures.